Next I'm going to show you the inversion formula, how to go back from characteristic function to the distribution of a random variable. As a consequence, if the characteristic function is known on the whole infinite real line, that will uniquely determine the distribution. Before I state the inversion formula, just notation: from now on I'm going to use a distribution function, so this is a cumulative distribution function, and the notation mu interchangeably, namely if the probability that x is less than or equal to a is f of a, so in other words f is the cumulative distribution function of the random variable a, then I'm going to use mu of any set b that's Borel measurable, so it's in the Borel sigma algebra on R, to be the probability that x is in that set B. For example, if I take an interval that's actually open on the left and closed on the right, then this is just going to be FB minus FA. Okay, so this is just the Lebesgue-Stieltjes measure of distribution function f. So this I'm going to use interchangeably from now on in this unit. Okay, and then here is the statement of the inversion formula. So theorem, inversion formula, has two parts. Part 1, so okay, let f be a distribution function, cumulative distribution function. Mu is associated to f in the way I just explained above, and let phi be the associated characteristic function. Okay, so phi is equal to the integral from minus infinity to infinity exponential of itx dfx, as before, the expectation of exponential itx with respect to this distribution. Okay, and then I'm going to show you how to find out f from phi. So instead of f directly, I'm going to look at the open interval AB plus 1/2 a possible point mass at A and 1/2 a possible point mass at B. So the random variable could have some probabilities of taking a particular number. For example, it could be discrete or it could be something mixed. This is the quantity which I can explain to you in terms of the characteristic function. Namely, it is going to be the limit as c goes to infinity of 1/2 pi integrate from minus c to c exponential of minus ita minus exponential of minus itb divided by it, and multiply this by phi and integrate this over the variable t. This is for every a smaller b fixed real numbers. Okay, and part B tells you for something about the continuous case, namely if you're given your characteristic function, then you can ask about the integral of the mod of the characteristic function. If the mod is integrable, then the distribution function f is absolutely continuous. In other words, it has a density, so the random variable is continuous, and its density, it's a probability density function. Its probability density function is f of x equals to 1/2 pi integrate from minus infinity to infinity exponential of minus itx phi of t dt, and this is for any fixed x in the real line. if you've seen a an inverse Fourier transform before, that's exactly what it is. So we're really talking about Fourier transforms when we're talking about characteristic functions. Okay, so this is the statement of the inversion formula, and now I'm going to prove this statement. Okay, the proof will be a little bit of analysis. So part A first. I'm going to start off with, so proof of part A first. I'm going to start off with defining the following function of c, 1 over 2 pi, integrate from minus c to c, e to the minus ita minus e to the minus itb divided by it times the characteristic function dt. Notice that in the statement of the inversion formula, we're exactly taking limit of this function. Okay, so eventually we'll take limit of this function, but for the first part I'm going to fix c, and I'm going to just ask questions about this particular function. Okay, now let's put in what phi is. Phi is the integral of exponential itx df. Let's just put that in. Okay, so 1 over 2 pi, integrate from minus c to c, and then integrate from minus infinity to infinity, e to the minus ita minus e to the minus itb. So far it's just copying the first bit. And then, so phi itself was the integral. Phi itself was the integral of exponential itx df. So I have the integral of exponential itx df inside, and then dt outside. That's what I get when I plug in the characteristic function. And of course, mathematician reflex, I see a double integral, I immediately want to swap the two integrations. But the question is, can I swap them? And that's of course not very easy, or not straightforward always. So a little bit of detour. Can we swap? Can we swap the integration? Now Fubini's theorem comes to help, which I mentioned before. Now I'm using the analytic version, so the measure theoretic version of it, not the probabilistic one. If you have a double integration of some function, and if you put a mod around your function and it's still double integrable, then you can swap. So let's find out about the mod of exponential minus ita minus exponential minus itb over it, and then e to the itx. If this thing is double integrable, so integrate from minus infinity to infinity df minus c to c dt. If this double integral is finite, then we have the right to swap over the two integrations. So let's check this. Okay, so I'm taking a mod there, and taking a mod means that I can as well take the mod separately on the product, but the mod of the second bit is of course 1. T is real, x is real, so this is 1. I don't care about that one. And the first bit, if you check what the integral from a to b of e to the minus itx dx, but let's use another letter, let's use y here. If you check what the integral of exponential minus ity is, that exactly will give you that quantity there. And this thing is less than or equal to the integral from a to b of the mod of e to the minus ity. Just bringing the mod inside the integral, it makes it larger or equal. Okay, which is 1 integrated from a to b, so that's b minus a. If you now put the double integral of this, so from minus c to c, from minus infinity to infinity, b minus a and then df actually doesn't depend on x nor on t. So if you now put if you now do this double integration, the integral of df is 1 because it's a distribution function. The constant b minus a I can write out in front. So when I do that, when I put the constant b minus a in front, then integrate from minus infinity to infinity df, this is 1, constant is in front, integrate from minus c to c, the constant 1 gives me 2c. Is this finite? Yes, it's finite for every fixed c. So Fubini allows me, so Fubini tells me a big yes, we can swap the two integrations. Okay, so let's then do that, and let's then conclude that phi of c is 1 over 2 pi, the integral from negative infinity to infinity with respect to f, and then the integral from minus c to c with respect to t of exponential of minus it a. I'm going to bring in the itx inside this exponential here with a minus x. A minus x with a minus gives me a plus, and it's a product, so that comes out here. And minus the same for the other term. So b minus x divided by it. Okay, so that's what I got for the integral of the double integral that makes up for phi of c. Now this thing here in the middle, I'm going to denote, actually including the 2 pi, the 1 over 2 pi, and this integral in the middle, together, I'm going to call this psi of c. Obviously it depends on x, it doesn't depend on t because I'm integrating with respect to t. So with that notation, I find that I'm integrating from minus infinity to infinity psi of x dfx. Okay, what comes next is analyzing this psi. So what is psi? Now, psi is an integral in t, so a minus x is a fixed constant, b minus x is another fixed constant, and I'm integrating this thing in t on a symmetric interval, and at this point it becomes important that we're looking at a symmetric interval. What is exponential of it and any constant here? What is that? Well, that is cosine of t a minus x plus I sine of t a minus x. It doesn't matter that this is a minus x, any constant could work. Alright, now I'm integrating this in t, I'm dividing by it, so let's divide this thing by it. And I'm integrating this over a symmetric interval from minus c to c, which is a symmetric interval. The cosine function is an even function. It doesn't matter if I plug in plus or minus t. If I divide it by t, it becomes an odd function. Okay? If I integrate an odd function over a symmetric interval, that gives me 0. The sine function is an odd function, but if I divide by t, it becomes an even function. So if I change t to minus t, it doesn't change value. Integrating that on a symmetric interval will matter, but integrating the odd function of cosine t over t will not matter, because if I change the sign, cosine t over t swaps sign as well, and if I go from negative c to 0 and from 0 to positive c, the two contributions just cancel each other. So what I want to say here is that looking at psi itself, I can actually only look at the sine part of that integral. So psi itself, instead of looking at the exponential functions, I'm just going to look at the sine t over t part, which matters because the cosine t over t part cancels out, and that gives me 1 over 2 pi, integrate from negative c to c, sine of t a minus x over t and minus dt minus 1 over 2 pi, the same with b, sine of t b minus x over t, and integrate this from minus c to c dt. That's my function psi. Now, before I investigate this a bit further, let me just do a change of variables. I'm going to introduce a new variable, namely this one here. So t of a minus x is going to be a new variable u here for the first integral, and t of b minus x is going to be a new variable v for my second integral. It's just a constant multiple of t, and dt will have this constant multiple, and t will also have this constant multiple, so those cancel, and I just end up with 1 over 2 pi integrate sine of u over u minus 1 over 2 pi integrate sine of v over v. But then I have to be a bit careful with the integration boundaries. So if t was c, then u is going to be c times a minus x, c times a minus x, and here c times x minus a. And on the other side it's going to be c times b minus x and c times minus c times, well, c times x minus b. And I just realized that here I should have added a minus in front of all t's, and that brings me a minus in front everywhere here, and when I do the change of variables, that gives me a minus in front of these boundaries. Okay, so let's continue with this quantity. I'm just going to rewrite it again and make it a bit better to read. So I'm still looking at this function psi of psi of c is therefore, if I want to summarize, 1 over 2 pi. I even forgot a 2 here. 1 over 2 pi, okay, integrate from minus cx minus a up to minus cx minus a up to cx minus a, so that's going to be cx minus a of sine u over u du, sine of u over u du minus, and then 1 over 2 pi integrate from the same stuff in b, so minus cx minus b downstairs minus cx minus b plus cx minus b upstairs. You can still see that. Cx minus b, so minus cb minus x is plus cx minus b upstairs, sine of v over v dv. Okay, And now what I want to do is I want to take a limit in C. So eventually at the end of the day I need to take a limit as C goes to infinity in psi C. So what is that? Now, the function sine v over v is a nice function. If you integrate sine v over v, or sine, if you integrate from minus infinity to infinity sine v over v dv, that's just pi. That's a fact from analysis. I'm again not going to show this here. Everybody can look up how it's done. The function itself is a nice function. It's not defined at v equals to 0, but it has a limit at v equals to 0, and we can use that. And so it's kind of this oscillating function, and oscillating and decaying function. And when you integrate this function, the total area under the curve is pi. Moreover, the total area is behaving nicely. So as you integrate from one constant to the other, it's bounded nicely, and we'll make use of this fact a little bit later on. But let's get back to the integral we have now. The first observation I want to make: if x is smaller than a, if x is smaller than a, so that makes this guy negative, this guy negative, this guy negative, this guy negative. If I take c to infinity, then I have from positive infinity to minus infinity, and the same for positive infinity to minus infinity, integrate the same thing. This function is beautifully integrable, and I get a big 0. One value, which is pi, minus another pi, that's a 0. When x is larger than b, the same thing happens. When x is larger than b, the same thing happens. Namely, I have from minus infinity to infinity, and also minus infinity to infinity, my integral, and then the whole thing is 0. Okay? More interesting things happen when x is a. What happens when x is a? When x is a, then x minus a is 0, x minus a is 0. I'm integrating a nice function on a 0 length interval. That doesn't give me any contribution. And notice that a is smaller than b. We're always looking at a smaller than b. So when x is a, then I have a minus b here, which is negative. So this part is positive, whereas a minus b is negative. So I go from positive infinity to negative infinity. I can use the minus sign to swap that around, and then in total I have a adding from negative infinity to positive infinity. The integral is pi. I'm dividing that by 2 pi, so in that case I have just a 1/2. Okay, so if x is a, I have a 1/2. If x is b, what happens when x is b? Then this integral has no contribution. B minus a is positive, b minus a is positive, so I go from minus infinity to plus infinity. The total integral is pi, divided by 2. Again I have 1/2. So either x is a or x is b, I do get 1/2. Finally, if I take a number x strictly between x, a and b, what do I have then? If x is between a and b, then x minus a is positive, so minus infinity to infinity, I have pi over 2 pi, so that's a 1/2. And then I subtract the integral from, so x minus b is negative, so this gives me a positive infinity, this a negative infinity. Going from positive to negative infinity with this integral gives me minus pi, but there is another minus in front, and a 1 over 2 pi, so that gives me a minus negative 1/2. In total I have 1. So this phi of c has a nice limit as c goes to infinity. So now I'm almost done. Let's recap what we are doing here. So we want to look at phi of c, okay, we want to look at phi of c. Phi of c is 1 over 2 pi, not even 1 over 2 pi, it's just the integral of phi of c, or of psi of c. So phi is the integral of psi, okay, with respect to distribution function. And eventually I'm going to take phi to infinity, because what I want to look at is the integral of this exponential business times phi. So this was capital phi, but I want to take eventually c to infinity. That's why I was looking at this formula here. So what I really want to look at is the limit. What I need, let's change color again. What I need is eventually, is the limit as c goes to infinity of phi c. Okay, again, phi was defined like this. Phi was defined like this, and in my statement I claimed that I can take a limit of that quantity, and that should give me this mu expression there. In other words, what I need is the limit as c goes to infinity of, so what was phi? Phi was the integral of psi. That's what phi was, the integral of psi from minus infinity to infinity. That's what I want to find out. It was with respect to df. And now what I did so far is I concluded what the limit of psi is. So I concluded the limit of psi. However, this limit is outside the integration. So I'm not completely done yet. Okay. The next observation I want to make is that this psi here, the integration of sine u over u, and that's what I mentioned before, integration of sine u over u behaves nicely. It's never going to blow up. When you integrate a symmetric interval, then this will never blow up. So this psi has an absolute constant in it. Psi of c, there exists some k, this is purely analysis, nothing random here. There exists some k such that psi of c is bounded under k for every x. No matter what x is, for every x there is a common k, so that we have this bound. This is uniform in x. And therefore we can apply a bounded convergence theorem, which will bring this limit on the psi in and out the integration. So before of this and before of bounded convergence or dominated convergence, this is actually equal to the minus infinite integral of the limit as c goes to infinity of psi of c. But that limit is exactly what we calculated up here. So this limit is 0 outside a or b, so I have no contribution when my random variable is outside a or b. This limit is 1/2 at a and at b, which means that I have this 1/2 contribution if there is a positive measure given on df at a, that will count with a 1/2 contribution because of this 1/2 here. And on the open interval I'm contributing with a full weight, with full one value of the psi. So that gives me the term mu of the open interval a b. And that's the end of the story. Because now you see how my left hand side in the original statement comes up from this limit here. I exactly have 1/2 of mu a, so half mu a, half mu b, and the open interval, half mu a, half mu b, and the open interval. So that's the end of the proof for part A. Okay. So let me proceed to part B, and this was page 3. Let me just put that in. So let me proceed with part B. And I'm going to remind you in a second what we need to prove for part B. So proof of part B. What do we want to do in part B? So part B was this statement here. If the characteristic function mod is integrable, then we have absolute continuity, and this is the formula for the density. So let's try to prove that. At this point, I'm going to define f of x to be the function 1 over 2 pi integrate minus infinity to infinity e to the minus it x phi t. This is a well-defined integral if phi is integrable. And moreover, you can convince yourself that this is continuous. It's a continuous function. I'm not going to do this right here. If you want to convince yourself it's continuous, you just want to show that if you converge with some sequence to x, then this integral will converge, and you can do this using dominated convergence. I'm not doing that here. What I'm doing is I'm going to look at the integral of this function here. Okay, so I define this function. I don't know what it is, but I'm going to look at the integral of it. What is that? That's 1 over 2 pi, the integral on a to b of this function f, which is yet another integral, e to the minus it x phi t dt. That was my function, and then I'm integrating this function with respect to x from a to b. Okay, and the question, of course, is again whether I can swap the two integrations. Mathematician reflex, I see two integrals, I immediately want to swap them. So can I do that? And the answer again is that if I can integrate from a to b from minus infinity to infinity mod e to the minus it x phi t, if I can do that, if this is finite, then we can swap. This is Fubini again. Okay, and the answer is that this is fine, because under the mod I don't really care about the exponential function. It's just 1 under the mod. The integral of phi is by assumption finite, and that was the assumption we made in part B. The integral of mod phi is finite. So integral from minus infinity to infinity mod phi is finite. This finite integral only gives a factor b minus a, so this is fine. Fubini allows us to swap, and if we do swap, then let's see what we get. 1 over 2 pi integrate from minus infinity to infinity, integrate from a to b, and then e to the minus it x dx, and in fact I can already factor out the characteristic function here in the t integration, because that doesn't depend on x. Now this integral is something I can calculate. This integral is something I can calculate. Let's do that. So that's exponential of minus itx over minus it taken at b minus a. So exponential of minus itx over minus it taken at b minus a. That's what this integral is. Okay. However, if we just go back to what we did, or maybe part A of this thing, so we know that this integral exists. This is a nicely integrable function because Fubini makes sure that everything here is well defined, and therefore the negative infinity to positive infinity integral actually is coming up as a limit like this, or actually in any other limit. In particular, this symmetric limit in C will also give us the same exponential integral, the same integral here. So this guy is the same as that guy, and therefore it's equal to this combination there. So what I end up with, based on part A, is mu of AB plus half of mu A and the point itself, and half of mu B itself, and this is true for every AB. So what can we conclude from this? On the left hand side, this thing depends continuously on A and B, whereas this one is not a continuous function on A and B. If I change A a little bit, and if I had a mass in A, changing A a little bit will make a jump out of this, which means that I actually do not have any point mass at A and at B, because that would make the right hand side discontinuous in A or B, whereas the left hand side is continuous in A and B. So I don't have any of these point masses, can't have these, cannot have these because of continuity. In other words, my distribution cannot give masses on individual points, it can only give masses on intervals. And if it only gives masses on intervals, this was exactly the probability that my random variable is strictly between A and B. That's how I defined mu. And what I found is that the integral of this function here is exactly giving me the probability that my random variable is over that interval. That was the definition of a density. So at this moment I can conclude that f is the probability density function PDF of the random variable x, and that's exactly what the second part of the theorem said. If we have this condition, then f is absolutely continuous, and this quantity here is the density. So that quantity here I started with is the density. That's what I wanted to prove.